It is March 5th, 2026, and this is Journal Club. It is 8:05. The paper that we are doing is outside of our comfort zone, and by our, I'm using the royal plural here. Um, the paper is about little red dots, which is what I'm seeing at the moment, and could be black holes in disguise. So, little red dots as young supermassive black holes in dense ionized cocoons. Cadence and Giuliana asked if they could do this paper. I told them that I wouldn't be able to help them at all because I'm not going to be able to understand it. But a little change of pace, they thought would be kind of cool to do. So this is Rusakov et al. And who's the corresponding author here? This is from Manchester. And it is Rusakov. Interesting. I think in physics, they do their authorship on papers different than in bio, where it's not like first author, corresponding author. The corresponding author is the first author, I think. Take it away, folks. And I'm going to mute myself, and you probably won't hear from me again because I don't know anything about this. Bye.
Okay, so I'm going to be sharing my screen. So just when I start sharing it, someone tell me if they could see it or not. Okay,
Um,
can everyone see my screen?
Yep.
Yeah, you're good.
Okay. So like Char said, we are going to be presenting on little red dots as young supermassive black holes in dense ionized cocoons. Okay, so what is the structure of a black hole? So black holes, like going off of this diagram right here, are made of an accretion disk, which is a hot rotating gas producing emission. It like doesn't stop emitting gas, it's continuous, and it moves towards the center of the black hole as it's like gaining energy. Um, then there's the innermost stable orbit, which is the closest point where a particle can like orbit a black hole without being sucked in. Because like a common thing about black holes, we know that like closer an object gets, it's going to get like eaten by the black hole. So that's the farthest that something can be stable without getting sucked in. And then there's an event horizon, which is the boundary surrounding a black hole. So the point of no return where not even light can escape. And then we have the jet, which is powerful beams of plasma radiation that blast outwards from a black hole at near light speeds. And then there's the center, which is the singularity, where matter is crushed into a zero volume point. Okay, so what are LDRs, or sorry, what it's supposed to say LRDs, which are little red dots. So they're extremely red bright sources that were photographed by the James Webb Space Telescope, or the JWST, at a very high redshift. So their redness is not like due to distance, it reflects intense heating inside of a thick cocoon of ionized gas surrounding a central engine. So nature explains that these dots are like young black holes surrounded by clouds of dust and gas that consume gas at extreme rates, causing them to absorb shorter, bluer wavelengths in the infrared wavelengths, which is where the redshift comes from. It's important to know that they are small compared to typical galaxies, but they're very bright, and their spectras are hydrogen and helium emission lines, which are signatures of fast-moving gas near a black hole. And they appear in earlier cosmic history, like the time of the Big Bang Theory, and they're expected to produce the massive black holes. Why they matter for black hole formation is that they may represent black holes in a rapid growth phase, accreting gas at or above like the speed of light, and they are smaller than previously assumed, about like 100 times less massive than typical like celestial objects, also known as like, I think it's called quasars, which is a very luminous and distant active galactic nucleus, which is powered by a supermassive black hole. And then the cocoons of LRDs are like hiding most of the direct emission, so that's why they appear as red and why we couldn't notice them until the JWST photographed them for the first time. And the cocoons make them look red and compact, and Cadence is going to explain how the cocoon works.
Okay, so we don't really like it's not like a proven, it's more of like a model of why we couldn't see the little red dots before and like why they are red. Um, so black holes are surrounded by a very dense spherical shell of ionized gas, which means there's electrons and stuff in it, and the gas is very thick. Um, since the cocoon is Compton thick, which means it's an environment where gas and dust are so dense that they scatter and absorb most of the X-ray radiation emitted from it, which is why it hides from standard detection, which is why we haven't seen them before. The cocoon is like kind of a nursery for those black holes to grow, so like they grow a lot faster than when like black holes don't have the little red dots around them. And then because they have the cocoon, they kind of stay hidden and can grow at a fast rate without being detected until they're like full grown black holes. You can go to the next slide. And then this is a brief summary of the paper. It's kind of a lot, but I feel like there was a lot to like unpack in this paper. So the first part of the paper was firstly to identify what these little red dots were. They were first spotted by the James Webb Space Telescope, and they found out that they're rapidly growing young supermassive black holes. Um, this was kind of a theory that wasn't at first accepted because the mass estimates were different than what we originally thought. Because at first we thought that the black holes were too big to host galaxies, but this paper we found out that they're actually 100 times less massive, which means that they can host these galaxies. And then they talked about the cocoon concept and the X-ray, why they didn't show up. I didn't really go into that because I just talked about that in the last slide. And then this is a big part of it because of like cosmic evolution, because we were kind of missing and we didn't realize that they could grow so quick. And this shows that like they have that instant where they grow very, very fast in the first billion years of the universe, which is like a big finding because there could be more growing rapidly like right now, and we would have no idea till they're full-grown black holes.
Uh,
That's all.
okay, I have a couple questions then. Could you, for just to bring everybody up to speed, what is a supermassive black hole?
Like a bigger black hole.
Why are they important? You can say I don't know, and then I'll answer.
I think they're important because they're like they can hold galaxies like versus like the black holes that aren't supermassive can't host other galaxies. But I
Is
could
Okay.
be wrong.
isn't it because like they just like shape the other ones, if that makes sense? Like they're the energy behind making galaxies.
They are the center of galaxies.
So is it kind
All
of like how the sun is like the center of our solar system, but like
we found that all galaxies have a black hole at their center, but not just any black hole. It has to be. I think I want to off the top of my head. It's something like 2 million suns worth of mass. It has to be something really enormous. Okay, but my next question. Okay, so it's the center of galaxies. Why is this? Why is what missing? What was missing? You said that it provides a missing link, but what was missing? I You didn't say what was missing. It's the missing link for to explain what? Like what was the problem?
We weren't sure like how they were developing so fast. And it we
How
were
how
also
what how what wasn't developing so fast, or how what was developing so fast?
black
You said
holes.
it.
yeah, it was like how the supermassive black holes form so quickly because they're supposedly around the time of the Big Bang and we didn't know like how they formed.
What's the problem with that?
Because it's
Is it
scary not knowing
No,
what's around us.
no. So okay, the reason I'm pushing you on this is that actually The answer to that question is why this paper is interesting. And it's one of the few crises in cosmology right now is explaining they've got the Hubble and the James Webb and a couple other the Chandra telescope or whatever. They're looking out in deep fields. Okay, they're looking as far away as possible. And at the edge of the universe, as far as they can see, now the edge of the universe is also looking back in time, right? Because for, every light year away is a year that the light takes to get to us, right? And the estimates of the universe's size are somewhere around 96 billion light years. That should be a problem for you. You should also have an objection to that. How can, right? How can the universe be 96 billion light years across when it's only been around for 13.8 billion years? Anybody ever wonder that? Wouldn't that require that space is space is expanding faster than light, right? It's only 13.8 billion years old, but it expanded from nothing to 96 billion light years. Then how did it how did space travel faster than the speed of light? And the answer is that the speed of light is a speed limit in space through space, but space itself can actually expand faster than that. Okay, one. Two, in the beginning, this is the cool part. In the beginning, when the universe banged, everything banged all over creation all at once at the same time. Okay. It wasn't like some central point that then expanded outwards. It was everywhere. Everything came into being at the same time. But it was so hot. It was like over a gigakelvin. It was over 1 billion degrees Kelvin. It was so hot that atoms couldn't form. But eventually it cooled down enough that they did form. And that took about, I want to say 400,000 years, something like that. About 400,000 years after the Big Bang, the universe cooled enough that space became clear. It was no longer orangey fuzz, and it was cool enough that atoms can form and all this other stuff. But the only atoms that could
Wait, I have
form
a
were,
question.
yes,
So you're saying that space was just ma like this one matter until it cooled enough? Or
space had space had matter, but it was all quarks. It was like a quark. They called it a quark soup. It
like
was all
there was no like difference between anything. It was just all the same.
Yep, it was all the same stuff that makes up protons, neutrons, and eventually electrons. It was all
Oh.
fundamental particles. Eventually, it cooled enough that a proton could attract an electron and become hydrogen, but that's about it. So everything in the universe was made of hydrogen, and there was so much of it that they kind of condensed under, we think this is now the theory, right, that they condensed under their own kind of gravity and weight to become the first stars. And the first stars were the most massive, gigantic, like the stars were way bigger than our solar system, like they were huge, and they only lived like, I don't know, a million years, and bam, they go hypernova and explode. And only in those explosions can you create all the rest of the things on the periodic table of elements. Okay, cool, fine, whatever. Here's the problem: if the universe only cooled enough for it to be clear about 400,000 years after um, the Big Bang, how is it that within only, I know this is going to seem a lot to you, but it's not in cosmic terms, only 600 million years later, not only did we have stars, 600 million years, right? Not only did we have stars, but we had full galaxies already. The oldest galaxies we've been able to see with James Webb are like 600 million years old. How is that possible? How can galaxies form that quickly? That's the missing problem. Do you see? The reason this paper's in Nature is because they may have actually figured it out.
This is like off topic, but not. But I saw this theory, I forget where, but it was like that there is no other life forms because life was never supposed to exist. Like it was just like a disruption and like we happen to be created and there's like no life anywhere else because we were never supposed to like exist. I don't know. I just thought it was cool. Like you talking about that reminded me. That
The
might
other
be
theory, the other
ridiculous,
theories like
but
what's it called? The Fermi paradox, where are all the aliens? If there are so many other planets, how are there not aliens, and how come they haven't contacted us? Which is kind of timely because 2 weeks ago, Barack Obama let it slip during an interview that aliens were real. Did you guys hear about that? On a podcast, President Obama was asked, "Are aliens real?" And he said, without any joking around, he went, "Yes." Now we don't have any. We don't have them in storage at like Area 51 or anything like that, but yes, they are real. And then just moved on. And the guy never asked a follow-up question.
Are aliens real?
Uh, they're real, but I haven't seen them, and they're not being kept in what is it?
Area 51?
Area 51. There's no underground facility unless there's this enormous conspiracy, and they hid it from the president of the United States.
the government hid it from us.
Anyway, so what's the problem here? Galaxies that are far too young. They should not have been able to form that quickly unless there's some other mechanism. Go.
Okay, would anyone like to do figure one?
I can do it.
Okay.
Okay, so figure one, it just like shows images and data of several objects called little red dots, which is what we're talking about. And it was discovered by the James Webb Space Telescope. And these objects appear as very small, bright red points of light in deep space images. They come from the very early universe when the universe was only a few 100 million years old. And then the figure has two main parts. The first part is the telescope images, which it actually shows images taken by the James Webb Space Telescope. And in these images, the objects appear as tiny red dots surrounded by faint galaxies. They look red because their lights have traveled for a very long time through the expanding universe. And as the universe expands, the light stretches into longer red wavelengths and a phenomenon called redshift. And then the second part is the light analysis, which it shows graphs of light spectrum from these objects. And the scientists analyze this light using a method called spectroscopy, which breaks light into different wavelengths instead of appearing of simple dots. The data becomes lines and peaks on a graph that represent different wavelengths of light. And the graph displays strong and very wide emission lines from gases such as hydrogen and helium. And the shapes changes from a round dot in the telescope image to tall, wide peaks on the spectrum graph. These wide emission lines mean that the gas around the object is moving extremely fast, which usually happens when gas is orbiting or falling into a black hole. And from this data, scientists learned that these red dots are not normal galaxies. Instead, the evidence suggested that they are very young, supermassive black holes that are rapidly growing. They are surrounded by dense, hot, ionized gas and hidden inside a thick cocoon of gas. This gas both feeds the black hole and hides it, allowing it to grow very quickly in the early universe while making the object appear as a small red dot instead of a large, bright galaxy.
Why are they red?
So I'm gonna tell the truth, I don't know why they're red, but I also questioned it.
I mean, she
Anybody else?
said before that the wavelength that's emitted, I think, was originally blue, and over time the wavelength just gets stretched out into red, which she said it was redshift. That's what it's
Yep.
called.
So what is that?
What is redshift? Or
Mm-hmm.
isn't it just like the wavelength being stretched, like the energy, like over time as it like travels through space? So like to us it's red, but
Yes.
in reality it's blue.
No.
No? Okay.
No, you were good until there. It actually is red, but why is it why is the light wave being stretched out?
Is it like not because it takes so long to get to us, or
Is
Is
it
it just
getting pulled towards the black hole?
So remember, I said that in the Big Bang, everything started as like kind of a small area and then banged all at once everywhere at the same time. And when that happened, the universe expanded the equivalent of going from like the size of an atom to the size of our solar system in less than a femtosecond or something crazy like that, like 0.32 zeros to the one something like that. It was able to expand that fast and it kept going. Because space is expanding faster than light, it's causing the light wave to stretch out. So I went and grabbed Lizzie's slinky. Okay. So imagine that at first, this this photon is traveling through space. Okay. It's traveling through space. But over the eons, space itself has actually started to stretch, right? And so its wavelength stretches more and more. And so you started with a really, really high frequency wave, but instead now it's all stretched out. And the longer it gets, the more red it goes on the Roy G. Biv spectrum. Cool.
so is
That's
it like the
redshift.
brighter the red, is it more, does like the longer the wavelength have anything to do with like the energy behind it?
So yes, but I don't think the way you think. So I think the key point to answer that question is they did say it started as blue. So the closer you would get to that, like if you started traveling closer and closer to the speed of light towards one of these galaxies, it would start to shift. It would start to blue shift. It would shift back, and you'd start to see it in its original color. And blue, so here's the answer: blue is extremely energetic, right? Because if you think about a wavelength of this distance from here to here, right? Look at how many waves I was able to fit into it, right? Much higher energy than if in that same distance from here to here, I only have two, right? So blue, ultraviolet. I mean, you keep going on the spectrum. We did this for photosynthesis, but yeah, it's so that's the red shift. Why everything seems red.
Okay, would anyone like to do figure two?
I can try. So the in A, well, the title says the HA with like the A is the alpha, so it's hydrogen alpha. No, Char has a weird face. Is it not? Because in the bottom it said emission line. So
I
I
think
think
he's just trying to read the graph. I think he's just squinting.
I
He's
don't know.
just
I just
old.
thought it was weird.
No, I was just thinking the way you put it. You said hydrogen and it's the alpha, and I was like, what does that mean? It's
Well,
a
no, because I
type
was
of
trying to say like H and then like the weird A. Oh, you
oh,
guys
it's an
can't see
alpha. I
it. I
see what
was
you mean.
looking at the
Okay.
paper.
Oh, okay. All right.
It says it on the paper.
Mm-hmm.
But the blue line is like the exponential group, and then the black dots on it is the data that's observed for on the emission line. And I don't know how to say that word with the G, the
Gauss,
Gaussian,
yeah, Gaussian or Gaussian, yeah.
Gaussian. And it just shows that like it's like way different or like staticky compared to the exponential one, which shows like the light is thrown off, I think.
Yeah, so like the Gaussian is the one that like we expected with like the bell-shaped curves. And then the one on the top was the one that we actually got.
Yeah. And then in B, uh hello. My thing is freaking out. But in B compares to the left and right sides of the line. Both show similar exponential drop, supporting the idea that the light is being scattered by a dense cloud around the black hole, like with the emissions. Maybe.
I have no idea what these graphs mean. This is
Yeah.
way over my head.
I don't know. I was just going off what's at the bottom, but that's what it sounds like.
I think for graph A, like it was kind of showing what we expected to find if like the little red dots weren't there. And then since we found, because in one of the other slides we were talking about how it ended up being like 100 times more massive, I think. So like the
Less.
bell-shaped curve is what we expected because of like the gas around the black hole. But it was like it didn't end up matching because it like it was exponential because like the cocoon it scattered everything, I think is what that's saying.
What's F
Where?
of the y-axis? It's labeled F. F lambda over F lambda max. I know what lambda is, but what's F?
I don't know.
So lambda is in physics, lambda is the wavelength.
I want
It's
to
saying,
say that's what was used to like measure the size of the black hole, I think.
Isn't just like intensity the light?
well, intensity is a function of wavelengths. That's possible, but can someone tell me what F is? I don't know what that is. It's not referring to object F from figure 1, is it?
I don't think so. I don't know. I couldn't find it in below. I couldn't find where it talked about F. Like at all, like what they used for their X and Y axis.
I searched up the best thing I could find is that it means flux per unit wavelength. I had no idea what that means.
Oh,
I mean, that's what it says.
that probably is it. Oh, okay. Okay. How much variation is there from a baseline in the exponential versus the Gaussian? Okay. That's that still doesn't help me understand it, but okay, at least I know what that is. Okay.
Is it just like a comparison graph to be
It
like
is.
is it just more exponential, meaning like it scatters and it's not normal, whereas the
Right. And
Gaussian one
so,
is?
well, I think what Cadence was saying was that it was that they were been predicting that it'd be 100 times more massive, and they just didn't understand that was possible. And the exponential is not as robust; it's squished, showing that it's not. I have no idea if I'm interpreting that right because I don't know how to read this. Cool. Moving on.
Does anyone want to do figure 3? Have fun, Andrew.
All right, figure three. So, we have a lot of graphs as you can see. All of these are really just representing how much hydrogen light, H alpha, it says it down in the caption, is coming from each of the red dots they found. So on the x-axis, as you can see, you have the wavelength, and then the F maxing. It is what it is. Don't really know what it is, sadly. Um, Now
Well,
see that
is it fiducial?
it says fiducial scattering model.
So does F mean fidu? I have no idea what fiducial means. I know
Um,
what fiduciary is, but what's
I would
fiducial?
not know.
so can I
Yeah,
say
go.
something? So I did look it up on ChatGPT. So apparently it's called the flux. So
Oh, that's what
the
Andrew said.
oh
Fiducial means it's a fixed basis of comparison.
okay.
What does that mean? I love learning new things. I am not negative about you doing this paper at all. I'm quite entertained, but I have no idea. I'm so out of my element. I have no idea what that means. Say it again, Cadence. The fiducial means
It was like the fixed
a
basis of
fixed
comparison.
basis of comparison. What is
So
that?
they
Fixed
probably had like a certain number that was like the average, and then like the graph shows how much it fluctuated from the average, I think.
Which is what Gaussian is. Okay. Okay. This is how we learn. Okay. Cool. Cool. Kira's comfortable. That's good. Like she's got like what do they call those blankets you would wear around?
I'm not
What?
wearing it.
Whatever. All right. So and Andrew, these were just the different objects.
Yeah, I was just got the graphs. So the graphs, again, like I said, it shows hydrogen light coming from each of the red dots, X axis wavelength, F max, Y axis. So you'll see in these graphs you have the dots measured below. So below all the curves, you can see little dots, which are measured from the James Webb Telescope. And then and you'll have those all those, little curves at the top. However, you'll see in some of these that there's orange and pink lines. So that orange line means how much hydrogen first came from the dot itself, how much hydrogen was actually coming out of that red dot, which could be a black hole. The pink line shows um how basically when this hydrogen light starts, coming off the red dot, how the electron scattering spread the light outward. The pink and orange lines are basically like a model for that's been like calculated and found by the scientists to compare it to what the actual telescope found. And the blue line is just, a final observation and um model of the pink and orange lines. And you'll see in the legend it says for the orange line, lambda 6549 6549, and for the pink it says lambda 6585. If you compare these to object K and object S, you'll see that they actually have very similar numbers to these graphs right here, to these points on the graphs. And that's kind of weird because, as you can see in the caption on the actual paper, it says H alpha line profiles for the full sample fitted with the whatever fiducial means scattering model. H alpha basically it's hot ionized gas. I searched it up. It says hot ionized gas, and it's actually found a black hole, which is kind of what's concerning because if they're finding all of this gas and it matches very well with these pink and blue lines in that final model, who knows? Maybe those red dots could actually be a black hole, and that's all. That's really what Figure 3 is trying to show here.
Yeah, but as we said when we were talking about the history of the universe, what is once everything cools off enough, what gets created?
You said it was like a new universe, right? Like a galaxy.
No, 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 no. So,
The
okay,
atoms,
atoms of what?
fundamental matter.
Yeah, yeah, yeah. Wait, atoms atoms are fundamental elements of matter, sure, but which one
Hydrogen.
specifically? Hydrogen. Pretty much just hydrogen. So hydrogen is the most abundant element in the universe by a lot. I always thought that it was something like 97 or 98% of all matter in the universe is hydrogen. So it's not really surprising that it's around black holes. I think I'm wrong. Somebody check me though. How much of the universe is chemical matter is hydrogen? But also, can I, Juliana, surrender your screen for a second? I want to share mine. Show you something.
Roughly 90% of the universe is hydrogen.
How much is helium? 8?
Helium, it says Well, composition by mass says approximately 73 to 75 is hydrogen and 24 to 25 is helium.
Okay. Hmm. Um, so just to kind of make this real for you, we actually have a bunch of these filters that we bought. Can you guys see this? Right. We bought a bunch of these filters to go onto the telescopes that we bought, and they are designed specifically to isolate, first and foremost, hydrogen alpha. So you can see on this, let me see if I can make it bigger. Yeah. Right here, H alpha, and you'll notice that the emission line here is actually really, really high. And it's also really, really high for oxygen 3, so that you can use these filters to get rid of any type of light pollution, but still get the thing in the image. That's why the image of the Rosette Nebula looks so good. I was actually using this filter. Cool.
When you say like hydrogen, you mean how much, like, how can we see how much hydrogen is in like anything that we look at, like by just looking at it? Or is it like how much hydrogen is like coming off of what we're looking at?
I don't know if Miss Torrance does this in her physics class. She might, but you could take a pure substance and um, throw a bunch of energy into it, ionize it, ionizing energy, so like really high voltage electricity or something. And what it'll do is it'll glow, and every element has its own spectrum of light, so you know what its signature is. And so it's really easy to tell which one is hydrogen. And so if you can see that, I think you can then estimate its density based on what you can see through it, like stars shining behind a nebula, for example, will give you an idea of how dense the nebula is. But I think that, and also gravitational lensing. The more stuff is there, the more it'll actually bend space. So you'll see the same object that's behind it. You'll see it in multiple places around it. Does that make sense? It's called gravitational lensing. Wait, let's make it wild. Okay, here's a wild one for you. There is nothing in the laws of physics that stops us from creating a telescope that is so big it can look at a sequence of, say, supermassive black holes that have collected light from our sun over the years, and where the light from the sun has traveled out to that black hole and gone around the black hole and then is focused back at us, and it would be looking back in time. You'd be able to actually see our sun, and if it's like crazy technology, Earth back in time. It's like a time machine almost. Because if you look at the picture of the Orion Nebula that's hanging in my office, the light that we're seeing in that nebula left that nebula 1,500 years ago, when the Roman Empire was still around. So if you could just get Earth's light to go around a couple black holes and then focus back at us, you'd be able to see back in time. Crazy? Cool?
But like you would see back in time from the future back to now, not back in time
No,
to
back
like
in time.
the 50s.
Oh, way past that.
I'm confused.
Light travels at the speed of light. So we invented radios in the early 1900s. That means that the radio waves from Earth that have gone out into space, they're dilute. It's hard to pick up the signal, but they're still there. They will have gone about 100 light years from Earth by this point. But if you are 90 light years from Earth and you're listening, you would be hearing the Nazis in Germany, because they were the ones really, really projecting a lot of radio into space, and you'll hear like Hitler and stuff give his speeches, and people 90 light years from Earth would be like, "Whoa, these people are crazy," you know. but they're actually looking back. They're listening to a little time capsule
So maybe that's why we haven't seen any aliens, because they're all
because
scared to
we
come to
scared the
Earth.
crap out of them. Yeah, yeah, with our genocidal, homicidal. Yeah, maybe. Okay. Trying to make this interesting for those of you who, maybe aren't buying into it, but I think it's pretty cool.
So can I go back to screen sharing?
Sure.
Can everyone see my screen?
Yep.
Yep.
Would anyone like to do figure 4?
I think figure 4 was like kind of hard.
Yeah. I
So
mean,
like if
I could try, but like it's only like basically from the when I read the bottom, the black like lettered dots, those are the re like measured um data compared to the gray with like the better technology, and it's like 100 um times less
Yeah.
each
Yep.
for each thing. That's kind of all I got from it.
Yeah, and if you look at the X and Y axis, it's a logarithmic scale, and those symbols actually are kind of fun. It says M, which is mass, with the little star. That's actually a black hole. So mass of the black hole divided by the mass, and that symbol next to the second M actually means solar. One sol of mass, which is one sun's worth of mass. And if you look at the symbol for it, it's kind of cool because it's a dot in the center of a solar system. That's a symbol for one solar mass. And so this is just saying how much times the solar mass in a certain amount of whatever. So yeah, it's dropped significantly since the last one because it's a logarithmic scale. So each one of these numbers is 10 times more than the previous number.
do we know what the blue line is?
Uh, I think the blue, I think it's all of the observed supermassive black holes currently in existence. That so it's like kind of what we know exists. And you could see the problem. If the gray was correct, they're like way outside of our model.
Right? Like what were they thinking? Like because the
Well,
reobserved ones is the lettered ones, right?
right,
Those are much
and
closer.
much closer. What were they thinking? Well, I think that's kind of the point of this was that the miscalculations were caused by that cocoon.
Do they even have a way to like prove this though to be more than like a theory? Because I guess you couldn't really prove anything unless you were like in space.
Beyond my area of expertise, so I'm not sure. I have a couple theories, but I'd be pulling them out of my butt. I have no idea.
Okay, if no one else wants to add anything, we're going on to the conclusion then. So the implication of this paper, it just explains how black holes or supermassive black holes form so quickly and how they're actually hidden by the ionized cocoons, which is why they couldn't predict them before. And then, so the little red dots are just young, quickly growing supermassive black holes that are surrounded by the cocoons, and that hides their true appearance. And the first time they were photographed was like for this study. Our favorite new word is redshift, which is the stretching of light waves towards the red end of the spectrum. And then this paper does belong in Nature because of its implication on how supermassive black holes are formed, which we've been discussing throughout this whole journal club.
I would go further and say not just how supermassive black holes are formed, but how galaxies were able to organize in such a young universe, which was the actual crisis. We didn't know how that would be possible. I think we're in the third generation of stars in the universe. So, like our sun, which is a very, very basic, middle of the road, it's called a medium yellow dwarf star. Uh, Medium yellow, something like that, is a third generation star. So it actually comes from gases from a supernova that happened about 5 to 6 billion years ago. But that star must have come from the supernova of that first generation of stars that I said were the very first, groups of hydrogen that formed and they were really, 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 really big and just pure hydrogen and didn't have any metallicity to them. Huh. We are star stuff. Every bit of us is made in stars, except for maybe the hydrogen that was made in the Big Bang. That's possible.
I might be biased because like me and Juliana picked this paper, but like I thought this was interesting. Like sometimes I kind of lose it on like the biology stuff. But I feel like with this, like even if you don't know all the words, like you can still kind of understand it. Maybe that's just me.
I mean, like, I feel like we all went in with the same level because, like, you don't even really know it that well, Char. So we're all just like figuring it out together.
Well, other
Which, like,
people
isn't
can do
that
this
what
too.
the point of journal club is, though? Like, we're all supposed to kind of learn something new.
So generally, no, that's not the point of Journal Club, but it's the point of the Science Academy Journal Club, the way we run it. Yes, it is. So that's why it's fine. Yeah, I thought it was good. Anybody have any questions, comments? Did you have other slides? No? Okay. Let's see. So good job. Yay. Yay. Also the quickest that we've done. That was 47 minutes. Okay, Cadence, Juliana, good job, good pick. Yay. And we're now going into overtime.